Okay, so I want to give some preliminary considerations about some of these homework problems. For instance, the first problem talks about maximum gain. It says for each of the following systems, find the frequency omega m for which the magnitude of the gain is greatest. Now, just to give you a reminder, what this means is that if I put in e to the st, I get out 1 over 1 plus s plus f squared times e to the st. Right? So that's the complex gain. Now, when you're talking about frequency, you replace s with j omega. Okay. So that means that e to the j omega t is going to 1 over 1 plus j omega squared times e to the j omega t. All right. Now, when they talk about the gain, they're talking about the modulus of this. So we want to maximize the modulus of this, 1 plus j omega squared. Well, j omega squared is the same thing as minus omega squared. So that's going to be minus omega squared. Okay. So I'm going to maximize this modulus. Now, it's a modulus of a complex number. Now, to make this easier, that's the same thing as minimizing the modulus of 1 plus j omega minus omega squared plus j omega minus omega squared. Okay. All right, now you remember what the modulus of a complex number is, right? The real part of this, I'm going to write this as the minimum of 1 minus omega squared. That's the real part, and then plus j omega. Okay. So I'm trying to minimize this complex number. So I would just write this. So in fact, you can also just minimize the square, the modulus squared, 1 minus omega squared plus j omega squared. Now the modulus squared of a complex numbers has a particularly simple form, right? The modulus squared of a plus bi is equal to a squared plus b squared. Right? So you're just trying to minimize this this function, and it's a simple calculus problem. Right? So you can convert these problems to simple calculus problems just by remembering that you replace s with j omega. And you can also use this, trick that minimizing the inverse is the same thing as maximizing the reciprocal. And you're trying to maximize the modulus. So in this case, it's minimizing this modulus, and you might as well just minimize the modulus squared. Right? You minimize the modulus squared, you're going to be minimizing the modulus. Okay. So think about that, and that should help you get these problems just in a mathematical way using basic calculus. Okay, let's look at the second problem. The second problem says for a second order system with poles at -1 and -4 and no zeros, find the frequency at which the phase is minus 90 degrees using any method except for the vector method. Then illustrate and confirm that result using the vector method. So how do you understand this? When you have poles at -1 and -4, that means that the Laplace transform is going to look like something like a over, so it's s plus 1 plus b over s plus 4. And you can combine that, that's going to be equal to some constant over s plus 1 times s plus 4. You can do it either way. I think this is the best way to do it because you want to get a single multiplicative factor. Right? Now, what about this c? Well, I guess to do the problem, you're going to have to make some assumption about c. We'll have c not be complex. We'll just say c is real. And also, we should have to assume that it's greater than 0 in order to get the phase. Now, the phase of the response is equal to the complex phase of this coefficient. All right. Or you can say, when I say complex phase, it's the same thing as or the argument, complex argument. Right. If you write this in, so that's in polar form, right? If you write that in polar form, then it's going to be the argument of this thing. Right. Now, if the phase is minus 90 degrees, then what does that tell me about this number? Well, then this number would have to be in the complex plane. This number would have to be down here. So this is minus 90 degrees. So that means that this function must be a multiple of minus I. Must be equal to some multiple of minus I. Okay. Now remember, we're talking about frequency response. So if we have to do frequency, we'll also have to replace the S with j omega. So you're going to have to put that in here, and then you want to find out, and since the C is positive and real, we don't even need that. We can just say if this has a multiple of minus I. Okay, so what you want to do is replace this here and find omega such that your result is pure imaginary. And the imaginary part is negative. Okay. Now another thing you can say is if 1 over s plus 1, s plus 4 is a multiple of minus I, that's the same thing as saying that s plus 1, s plus 4 it must be a multiple of I. Because if you take the inverse of minus I, it's plus I. So if I take the inverse of a negative imaginary, it's going to become a positive imaginary. So plug in j omega, solve this, and set the real part equal to 0. And make sure that the imaginary part is positive. All right? So that's all you have to do. Okay, so the next one is looking at this particular system where the box represents a causal linear time invariant continuous time system. And we've seen system diagrams like that before. And it says determine the range of k for which the feedback system is stable. So what does stable mean? It means practically that the impulse response does not grow exponentially. Or it just says doesn't grow as t goes to infinity. Now remember, when you find the impulse response, so what you want to do here is you want to find the impulse response. Now the impulse response is going to be some linear combination of exponentials. And you need to make sure that those exponentials do not grow as t goes to infinity. So the exponential should not grow as t goes to infinity. All right, so this is an interesting question. We know that the exponentials will have the form e to the st. Now, what happens to this as t goes to infinity? Well, we can break s up into its real and imaginary parts. S real plus j s imaginary. times t. That's e to the srt times e to the j sit. Okay. Now, what happens to this? This will grow exponentially if SR is greater than or equal to 0, is greater than 0. Okay. So it decays if SR is less than 0. And it just remains constant if SR is equal to 0. All right? So what you want to do is you want to make sure that the impulse response, the exponents, have real parts that are less than 0. So the exponents of the impulse response should have real parts less than 0. All right, now what are the exponents of the impulse response? Well, that's exactly what the poles are. Remember, that's the reason we found the poles is that the poles give us the exponents of the frequency response. So be careful here. What you want to do is you want to solve for the system. Here, let me grab it again. Let me grab that again. Just the picture. So what you want to do is find the impulse response, and we can do that the way we usually do. Here we have from this plus, this node here is y. So here we have x minus y equals, I guess we take x minus y as the input here, and then we have x minus y times k over s squared plus s plus minus 2 is equal to y. And then you need to solve for y over x. Okay, and that's going to be some polynomial in S. And then what you want to do is find the poles. Or you can do, so the poles, and then that means the impulse response, and I suppose they're S1 and S2. So the impulse response is going to be some multiple of e to the S1t plus e to the S2t. So you just need to make sure that the poles have negative real parts. So, and that's going to give you a condition on k. So you want to find k such that the poles S1, S2 have negative real parts. Okay, so that's the relationship between stability and the poles of this impulse response. Now it's funny because it seems like this would be stable if k is small, because if k is large, you have a large gain, but that turns out not to be the case. So that's kind of an interesting result. Now the second question was determine the range of k for which the feedback system has real valued poles, and then that's just doing the same thing. So these poles here will be functions of k. Will be functions of k. Now, before I go on, I would like to mention 2 points that might be confusing. Previously, when we did the system diagrams, we didn't put a Laplace transform inside. We had blocks like the integral block and scalar multiplication. But Laplace transform is just the same thing. Just think of 1 over s as an integral block. Right? So this is representing some system that could be represented using the conventional circuit components. but we're instead of doing the algebra with the integral block, we're doing it with S. So the same rules apply, and this x and this y should not be considered as the Laplace transforms, and not as the signals themselves. So that's one thing. The other thing is that I did not emphasize, I hope you remember, but if you have a real part and the imaginary part is certainly not going to grow as t goes to infinity. The imaginary part is just going to be sinusoids. So we don't have to worry about that. We only need to worry about the real part of the exponent. Now, this next one for discrete time stability is very, very similar. We remember that in this case, the poles of the Z transform let's call them alpha 1 and alpha 2. Then that will give you, again, the system response, the impulse response, will be some constant A times alpha 1 to the nth power plus B times alpha 2 to the nth power. And if we're interested in stability, then we want these alpha 1 and alpha 2 to not grow as n goes to infinity. That alpha 1 to the n and alpha 2 to the n do not grow as n goes to infinity. But what does that mean? That means that alpha 1 must have absolute value less than 1, and so must alpha 2 has absolute value less than 1. So it's a different criterion. All right. So it's not that the real part is less than 0. Now it's that the absolute value is less than 1. So I would say, to be careful here, is that this k over z squared plus z minus 2 is not the z transform of the system. You'll have to solve for the z transform of the system by including this in the system and including also the feedback, just like I did for the previous problem with the Laplace transform. The second one, real valued poles. This has the same significance as with Laplace transform. If you have real valued poles, then the impulse response is not going to be oscillating. It will just be growing or decaying. Now, this next one relates to physics, and this is not a physics class, so let me set up the equation for you, and then you can take it from there. So this is a very nice problem. It has to do with what happens in your car, shock absorption. When you pass over a bump, there's springs in your car, and the springs are adjusted so that the car does not bounce back and forth when it passes over the bump, and it doesn't just rigidly feel the entire bump, but it cushions the bump. So that means adjusting the strength of the spring, and there's also something called a dash pot there that does some damping. So let me explain this diagram. So m here is the mass of the car, y is the vertical position of the car, and that's what you want to control. You don't want this y of t to vary too suddenly, and you don't want it to oscillate. Now the x of t is where the wheel is. The wheel is contacting the ground, so it's going to follow the height of the ground. So the x is the input, and the y is the output. Now, between the wheel and the mass of the car, you have this spring, and that exerts force, and you also have this dash pot that slows down the response. It does not allow the mass to respond too rapidly to the change in x. So what we have to do is translate these components into a differential equation. So let me copy this, and then I'll show you how that's done. I won't expect you to do that. I'll show you how that's done. So let me copy it here. So we'll just take the picture and the description and explain how this works. All right. Now, the basic idea here is Newton's law, which you probably have heard of, which is force equals ma. And this is force. Now, A is equal to, in this case, it's equal to d squared y dt squared, and I think he's using this notation as double dot. So y double dot of t is the same thing as d squared y dt squared. It's the same thing. Okay. So that's what ma is, so we have to get a hold of the force. Now there's two components to the force. There's the spring force. And this is proportional to the stretching of the spring. Okay. Now, what's the stretching of the spring? Well, the stretching of the spring is going to be y of t minus x of t. Now, let's consider the sign. If y of t minus x of t is big, then the force that exerted by the spring is going to want to pull y back. Okay. If y of t minus x of t is small, then the spring is going to compress. It's going to want to push y of t forward. So that tells us about the sign of this force. So if y of t minus x of t is big, if this is big, then the force will tend to reduce y, so we know that there's a minus sign here. Okay. So that's the force due to the spring force. Now we also have the, what they call a, I think they call it a dashpot or something. Oh yeah, dashpot. The dashpot is the velocity dependent force. So the dashpot force is going to be related to the velocity. And the total velocity of the dashpot is going to be the difference between the velocity of y and the velocity of x. Right? If they're both moving together, if the y and the x are moving together, there's no change in the dashpot because it's not this is like a piston. Okay. If both things move together, the entire framework is going to move together, so the piston is not moving relative to the frame. But the force is going to depend on the change in the y and the x. Now, we also have to think about the sign of this. If y of t minus x of t is growing, then the force is going to resist the growth. Okay? So that means that if I have a positive derivative here, I'm going to have a negative force here. So I have two terms of the force, and I'm just going to add them together. So I'm going to have minus k times y, I'll leave off the t's. Okay. Then I have minus b times y dot minus x dot is equal to my double dot. Okay. So that's giving me my input, my y. So you want to re-express. And I've said this before, that you want to have a linear differential operator, right, operating on y is equal to some other linear differential operator acting on x. Right? So this L is just derivatives. And then you can use this to find your Laplace transform impulse response and all that good stuff. Now this should be familiar territory from here. Okay, so the questions are, first question is, determine the differential equation. So it's going to have this kind of form that I showed here. So you'll have to give the L and the L prime explicitly. And determine and plot the impulse response of the system when B equals 0. So how do you get that? Well, you go to the equation. Well, you can go back to the previous notes that I did, how to get the impulse response from a differential equation. I did a previous video that talked all about that. And basically, you're going to look at the impulse response for different situations, different values of B, different values of M. And this is just, when B equals 0, so you can plot using Python. And think about what it's showing. You're going to show the impulse response, which will be a function of time, and that's what your car is doing. That's telling you what your car is doing. And that's telling you how your car is moving. So you want to tell, is the car moving in a good way or a bad way? So here he has three cases, when B equals 0, and then this is the so-called critical value for B, And then this is if b is very large. So you've got this here. He says sketch. You can do sketch or you can do plot, however you want to do that. Now this last one looks very complicated. Let me simplify things a bit for you. Although he says that the input function has two frequencies, in this problem we're just going to be looking at the column frequencies here. So here he says the buttons on a touch-tone phone generate tones that are used for dialing. Each button produces a pair of tones of this form. So it's a combination of two tones, and the two tones determine the row in the column. So we're just going to be looking at the column frequencies. All right. I mentioned frequency. This is cycles per second. You don't need to know too much about that. We'll get down into where we can talk about that in a minute. All right, so the problem concerns the design of a system to detect the row and column numbers that were pressed by analyzing the signal Rx of t. The following block diagram illustrates the basic structure of such a system. So in fact, you have 1, 2, 3 separate systems. You're not combining these three, so you have three different systems. Now, the input x of t is first sampled with t equals 10 to the minus 4 seconds. Okay, so that means that we are doing a discrete time problem, as you do typically with modern electronics, which is digital. Now, what does that mean? If t is 10 to the minus 4 seconds, and we are translating this continuous time system into a discrete time system, then what do these frequencies correspond to? Well, let's draw a picture. We'll go back here, and we will do our time axis here, where we'll have steps here. And each step is 10 to the minus 4 seconds. Okay. Now we have signals of the form cosine f1 of t plus cosine f2 of t. As I said, we're only going to be worried about the f2 of t, and I'm going to write this as a complex exponential. So we're going to have some signal that varies here, and it's going to, whoops, I don't know why I did that. So you're going to have some signal that's that is continuous time, e to the j times 2 pi omega. That's in continuous time. Okay. But my t here is multiples of 10 to the minus 4 seconds. So this would be n times 10 to the minus 4. And then this would be n plus 1 times 10 to the minus 4. So I need to replace t with n times 10 to the minus 4 because I'm only doing it at intervals of 10 to the minus 4. So replace t with n times 10 to the minus 4. Okay? So I'm going, the signals I'm concerned about are e to the j times 2 pi and then omega times 10 to the minus 4 times n. Okay? So in this problem, that's what those are the discrete frequencies that you're going to be looking at. Okay, so for example, we have omega 1, omega 2, omega 3. The values for these three omegas are 1209, 1336. And then the last one was 1477. And we're going to convert those to times 10 to the minus 4th, so it's going to be 0.1209, 0.1336, and then 0.1477. And we're feeding those into system, the three different systems with three different impulse responses. And we want to find a system that responds largely to one of the frequencies and not so large with other frequencies. Now, what he says is that each one of these is going to be described by two poles. So we have two poles here. So let me grab this here. So the question is, how does a system with two poles have a system with two poles responding to discrete signals of the form. So the form we have now, it's going to be e to the j, well, let's just call this, I'll call it omega prime n. And that's going to be my x of n. Okay. Now suppose these two poles, I could call this one, if this one is, I'll call this w, then this would be w prime. This would be w conjugate, right? So we could write this second order system as some constant divided by c minus w and c minus w bar. Okay, my w and my omega are kind of similar, but I hope you can see the difference there. Now remember that the gain is equal to the magnitude of this That's the gain. It's going to be the modulus of this complex number. And we want this to be large when the input is something like this. I'm sorry, we want this to be large for certain values of the input and small for certain other values. So the question remains, what do you put in for z? What do you put in for z? Well, z is simply this. This here is going to be e to the j omega prime to the n. So this is the z that you put in. Right? That's kind of that's like the s in Laplace transform, but for discrete transforms you put in the actual number that's raised to the nth power, and you want to choose your w to have the appropriate response. So you're going to choose 3 different w's to make this work. You're going to choose 1 w for each frequency to make this work. And then what does it say to do? Then we can go here, and you can plot the responses. So you'll be plotting the response to these single frequency signals. So determine values of r and theta so that it generates a large response for the 1 key and small for 2 or 3. Okay. Notice that 1, 2, and 3 are in 3 different columns. I don't worry about this next part here, but that's basically what you want to do. So you can also give the response to a key press. You can plot that. And okay, and then here, describe how the choice of R affects the output signal. You should say something about that. What are the maximum acceptable limits of R? What limits the minimum acceptable value of R? So please address that problem as well. Okay, that's it. Thanks for listening.